Okay, so we're recording again. Okay, take two. So the case here, it would be a secant because we have a kind of like a constant, a variable and a constant here. All right, so we'll have x, wrong pen. So x equals a secant of theta, and we get a, that's the square root of this guy over here. So that's 1 secant theta. And find the derivative of x, which is secant theta tangent theta d theta. Okay, so we have a replacement for this guy over here. So let's do the trig substitution. We substitute the dx. Replacement for dx would be our secant theta tangent theta d theta. Internet's disabled again. Might need to go downstairs. Oops. Then we have x is secant squared theta minus 1 to the 3/2. I think we were able to replace the secant squared by tangent squared. So secant theta tangent theta d theta. Then we have tangent squared theta. So let me know if you have questions. So this is, I'm just repeating what we've had so far. Then the squared got canceled here. All right, so we have secant theta tangent theta d theta over tangent to the 3rd theta. So as you could see, there's a tangent here and a tangent there. So that's kind of like a formula for canceling one of the factors, one of the terms. So you have secant theta over tangent squared theta d theta. Again, so this part is the tricky part always when it comes to this part. Okay, so what are some of the options? Okay, what is this thing? Oh, it's a red version of it. So we can try, I wouldn't recommend it, but tangent is 1 plus secant squared. I don't see anything going on here because you can't split them. The other one is make everything sine or cosine. So we can have secant is essentially 1 over cosine. And then, so this is the secant part. And the 1 over tangent is essentially, a tangent is 1 over tangent squared is essentially a cotangent squared. Yes, Mark.
Yes, it wasn't too long ago we subbed out secant squared theta minus 1 for tan squared theta. How is
Yeah.
it that?
This one, yeah. Oh, it's the wrong choice still anyway. See, that's true. That's my bad. That's supposed to be secant squared minus 1.
All right.
That's not a good choice too, because we can't split this fraction, and we're trying a different option. But that's right. Thanks, Mark. Is that what your is there a follow-up question to that one?
That was it.
Oh.
I have a question, Professor.
Sure.
Sorry. We can't split up the fraction. Is it because our secant squared theta minus 1 is not in the numerator?
Correct. It's not in the numerator. Had it been in the numerator, it will be an a minus b over c case. But right now we have a c over a minus b. That makes sense?
Yes.
Okay, so definitely not possible to split. We can kind of like separate them, like secant theta times 1 over tangent squared theta, where the 1 over tangent squared becomes a cotangent. So that's where we're trying to hit at this point. So we'll try that combination and see where it goes, because this is the tricky part. This is where students will try to experiment a bunch of different steps. Some of the options would work. There's more, in some cases, more than one option could work, but some solutions are kind of like longer than the others. So if we go from here, Let me just erase everything. Okay. Go back to the regular ink here. So we'll have integral of, I would say this is a 1 over cosine, because that's the secant. And that's 1 over tangent squared is cotangent squared, which is this one, d theta. The 1 over the cotangent squared is basically tangent is opposite over adjacent. So this will be, sine over cosine. So this will be cosine squared theta over sine squared theta. Make sense? All right. So in that case, this kind of like makes a little bit more sense because of the cosine here and another cosine over there, which we know could take out one of those cosine. So having done that, it's now a little bit cleaner. We have 1 leftover cosine in the numerator. We do have sine squared in the denominator, but we can actually split that as sine and another sine. Because this one is cotangent and this one is cosecant, which we have a formula. What is the antiderivative of cotangent and cosecant? Isn't that a negative cosecant? Theta plus c. So definitely very useful. Okay. So let's go to the next slide. Now, how do I paste stuff? So negative cosecant theta plus c. And we go back to the right triangle now. Our original relationship is, go back, we chose 1 secant theta over here. It's going to be using that again. So x equals 1 over secant theta over 1 over 1. We have secant theta equals x over 1. And secant is the reciprocal of cosine. So instead of adjacent over hypotenuse, this must be hypotenuse, and this must be adjacent. Okay. So hypotenuse is x, and adjacent is 1. And if you do Pythagorean, this will be square root of x squared minus 1. Kind of like is, it doesn't exactly look like this, but that over 2 there is the square root part. All right. Okay, let's continue from here. All right, so our cosecant here is 1 over sine, so that's hypotenuse over opposite. So we have hypotenuse over opposite, which is x squared minus 1 plus c. So it's actually simpler than I originally think. I will double check it later. I actually thought I had a longer answer here when I did this. All right, any questions so far? Did we miss anything? So if you're gonna go back on the previous slide, the critical point is this part. Yeah. Because that's kind of like had a couple of directions to go. All right, moving on to partial fractions. Let's go over one of the big ideas. Just minimize this.
Can we go back to the answer real quick?
Sure.
Yeah, Roxanne, we close notes from all of the notes from shops.
Okay, I'm gonna be uploading this, by the way. Do you have any questions on this one? All right. Cool.
Yeah, I'm all good.
All right. Okay, so now we're on another type of integration. It's called partial fractions. uh, I'm not sure. It's not as tedious as the other one, but it can be. It's more of a pre-cal. It depends on how big the fractions are, or how sophisticated the fractions are. So that kind of is proportional to the amount of work we'll have to do. So what's the logic behind that? If we have an integral where we can factor the denominator this way. Accidentally keep on clicking stuff at the bottom. Of this format, so you have something in the numerator. It doesn't have to be a constant, by the way, but you have some factors in the denominator. In this case, we have an x minus a and an x minus b. The logic of this is essentially we can split this up into two separate fractions of individual denominators pertaining to the actual factors. Okay. And we'll have a unique numerator for this and a unique constant numerator for that as well. And that's what we're hoping to get out of this situation. And that's why it's called partial fractions. We kind of decompose, we break it down into separate factors from a more sophisticated denominator to two separate kind of like fractions of simpler denominators. So the partial fractions themselves, they're actually from pre-cal. So we'll borrow from the pre-cal playbook here. Okay, so we have this one. So in this case, if we're just focusing on the fractions themselves, you can throw the 3 out if you want. So that's not going to be part of that anymore. Okay. So if we do that, we put the 3 here. This is just 1. We want the 1 over x squared minus x minus 30 to split into, well, before we do that, let's just break it down first into its factors. We can factor out x squared minus x minus 30 as x minus 6x plus 5, isn't it? So kind of like on the side, you have a trinomial, you look at the last term, you think of two numbers that multiplies to negative 30 but adds up to negative 1, which is the middle term over here. And the only thing that fits that description is negative 6 and positive 5. So negative 6 times 5 is negative 30, but if we add them, it's negative 1. Okay, it's a quick commercial break there. All right, so now that we have those factors, we want to decompose it, to break it into partial fractions. We have an a over an x minus 6, and we have a b, which is x plus 5. Okay, it doesn't mean that a plus b is 1. It's just some number. Okay. All right, so we'll start from there. And one way to do this is to actually multiply. It's a trick in arithmetic. We can multiply both sides by the whole denominator. Always. So this multiplies to everything. Okay. Cool. So this will cross cancel everything here. So this will cancel that. And so for the left side, we'll end up with a 1. Now on the right side, I'm not sure if I can oh. We have, we kind of like have the 6x minus 6 here and the x minus 6 there will kind of cross out. For b, the x plus 5 will cross out this x plus 5. So if we distribute the whole thing for a, for the a section, we will have a times x minus 6, x plus 5 over x minus 6, plus we have b, x minus 6, x plus 5 over x plus 5. Okay. Ooh, sorry about this. The pen is clunky. All right. So we know we can cross out this thing and we can cross out that thing. So the new version of the equation is a times x plus 5 plus b x minus 6. Okay. Kind of minimize the chat. Trying to look for it. So I couldn't see any of the chat right now. So somebody let me know if there is a question. Where is that chat box? Anyway. Okay. Okay, so no, there's no question. All right. So the goal is to solve for A and B. Okay. But how do we do that? Okay. All right. Because this is an equation, and x is a variable, and x could be any real number, we can assign predetermined x's that will be beneficial to us. What do I mean by that? I can choose any x that I want because x is a variable, right? This x here is the same as that x. But what would benefit me is to actually choose x that will cancel one of the other terms. For example, if x is equal to 6, I'm definitely sure that b will disappear because it will be 6 minus 6. So if I do that, I have 1 is equal to a, 6 plus 5 plus b, 6 minus 6, because I just chose 6 and it's convenient for me because this will be 0. Okay. And this is a times 11. And I can just isolate a by itself. So a equals 1 over 11. All right. Now, how do we get rid of B? I mean, of A. We will choose x is equal to -5. Okay. Any questions so far about the choosing of these things? Okay. So we have 1 is equal to a, -5 plus 5 plus b, -5 minus 6. So definitely this is 0. And b times -11, -5 and -6, -11, divided by -11 both sides. That will be our b, -1 over 11. Cool. All right. A question so far. Okay, so assume that is a good thing. A x minus 6. So we have a x minus 6 plus b over x plus 5, well, equals 1. That's what we had over there. And we got a's, essentially we got a is 1 over 11 and b is -1 over 11. So let me just kind of like rewrite that from the original setup. So we are now able to break this integral. Oh, by the way, I'm sorry, there is a 3 outside. Okay. Courtesy of this 3 here. So we are now able to break this entire integral into partial fraction. A over x minus 6 plus b over x plus 5. And we know that a is 1 over 11. And we have b, which is -1 over 11. X plus 5 dx. Okay, so far okay with this? So let me know. So some chat, I'm checking the chat once in a while to see if there are new things in there. Okay, so let me just write this better because this, I don't like to see complex fractions where you have like a fraction in the numerator and then you have it's part of a bigger fraction, you can actually make this a little better because that is something you can factor out. I prefer to see them this way, actually. Now that's going to be a minus now. 1 over x plus 5 dx. Because essentially, we will try to integrate them separately anyway. So we can write this now as a separate integral. So we're kind of integrating 1 over 11, 1 over x minus 6 dx minus 1 over 11, 1 over x plus 5 dx. So we just want to like treat them separately. It's easier that way. I kind of factored out the 1 over 11s outside the integral sign. It's a quick U substitution, just so you know. This will lead to an ln of x minus 6, and I'm gonna tell you why. So if we go do it the long route, so if we're gonna be doing the long route, so we have 1 over 11 integral of 1 over x minus 6 dx. Normally, we would just let u be equals to x minus 6, and du is the derivative of this, which is just dx. So definitely this dx is replaceable by a du. So this ends up with 1 over u du, which is just the ln of the absolute value of u plus c, well, 1 over 11 here. And u is x minus 6. So these partial fractions are very convenient in terms of getting the integral because they almost always end up with an ln of whatever the denominator is. The only sophisticated version of this is if one of the partial fractions, like for example, 3x plus 5, then your let u would be something else. Your du, I mean, is something else. So your du has a 3 dx in it. So that's legit u substitution.
How come we chose an ln for the substitution?
Oh no, we don't really choose it because that's just a good question. That's a very good question. That's just the result of this. We have a formula that if you have a 1 over u, the n of u, so they are inverse relationship, the derivative of n of u is 1 over u times the chain, or simpler, ln of x.
Yeah,
The
everything you
derivative of
just
that
said
is
did
1.
not pick up. It was all staticky.
Yeah. All right. Can you hear me? Were you able to hear that?
Right now, yes.
Okay. So it's just part of the formula, this thing here. Good question. Why did we pick it? Kind of like we're forced to do it. It's part of our formula sheet that the 1 over u is an ln of u because they're kind of like an inverse relationship. And derivative of ln of x is 1 over x. So the antiderivative of this is the ln. So any other question? I appreciate this. Kind of like stuck in this. Feel like we're in the first 45 minutes now of a very bad movie. Last time we met was just 30 minutes bad. It's a lot of things now. So this will end up as an x plus 5 ln if you do the same thing. Okay. In fact, let me just kind of like point out to you that anything x minus a ends with ln of x minus a.
Your voice is like really staticky right now.
Oh, sorry. I think it's the Zoom. Whenever we are too many in the room, it starts to kind of like become a bit choppy. But because I'm recording this, in the recording, it's clearer. Does that make sense?
Yeah, that makes sense.
Yeah, I'm really, really sorry for that. That's why we're trying this. Yeah, just bear with me. If worse comes to worse, I'll just record it ahead of time, and then I'll just keep the channel open. So anyone who's watching has to just go to me straight to the channel, and we'll just have a chat. But I thought that this is good because you can ask me question live. You can tell me any issue. Okay. Are there any other concerns? I'm kind of like moving closer to the router. doesn't really help, but maybe. All right. So that's the first case. So the first case is we have non-repeating denominators, linear denominator, keyword. So first, power, which can be decomposed into separate fractions called partial fractions. Now, the second case, which will be the last case we'll talk about today, is when we have repeating linear denominators. We'll go over the third case, but we won't solve anything in the third case. So the repeating linear denominators, you could see that this is a square. So essentially, this is the integral of x minus x minus a times another x minus a, right? These are duplicates, they're not the same. As opposed to this one, where non-repeating, these ones are repeating. We have repeating linear denominators. So we take a piece of the factors and we keep the square for the second one. So that's the formula. We efficiently break it down into partial fractions. We have to write the first power version, second power. If it's third power, we have to do them individually, like first, second, and third power. But that's too kind of like beyond our scope for today. Ooh. All right. So only if there are repeated factors. Non-repeated factors, that's just the simplest case where you just have to break them down into individual fractions. But because these are repeated, you have to incorporate a term, a partial fraction where the exponent is also a square. It's just the format we're following. It's the shortest way to solve this. It's the shortest way to solve that. Okay, so let's take a look at rearrange this thing. Okay, so let's take a look at this. Maybe we can pick one. All right. So we can rewrite this as the integral of 2x over x plus 3 times x plus 3 dx. So if we factor out this, that kind of looks like a repeated kind of factor. So definitely this will end up with a over x plus 3 plus a b over x plus 3 squared. Okay. Okay, so let's kind of like start working on that. Let me know if you have some questions over there. Okay. So we have the integral of 2x over x squared plus 6x plus 9 dx. We can factor out the denominator as an x plus 3 squared. It's a perfect square trinomial. And based on our rule, we can actually rewrite this as an a over x plus 3 plus a b, which is the duplicate factor x plus 3 squared, following this formula. So the factors do repeat, but the second factor, you have to square, otherwise they both cancel when you choose an x very, very quickly. All right, so let's split them. 2x over, you can throw the 2 out, that's not a big deal, but I'm keeping it here for now. So we want that to split into an x plus 3 plus a b over x plus 3 squared. Okay. So the original here is this one. We want it to be split into 2 fractions. Now, the trick that we did earlier is multiply everything by the denominator, which is x plus 3 squared. So multiply that to everything. We just write this into x plus 3 times x plus 3. Also, so the first one, it will lose everything in the denominator. The second one will only cancel one of the x plus 3. So a times x plus 3. For b, you cancel the whole thing. So both this and this. So you only get there a b. Are we okay with that? It looks simpler than the other example. So for b, it lost the whole denominator. And now we're free to choose x's. So if we say, I think the best candidate is actually -3 because that will zero letter A. So let's choose that. So if x is equal to -3, we will have the equation 2 times -3, courtesy of that, equals a times -3 plus 3 plus b. And we know this will zero out. We do get the value for b, which is -6. Okay. Oops, sorry. I'm gonna box the answer there. All right. Any questions? Check the chat box if there are some questions. Oh yeah, sorry, Elias and Adam. But the recording, so if you have some issues on some of the segments, just go back and replay that. I think it's just the limitation of the technology and internet because there are a lot of people in the room. It's the same as yesterday. We had the same issue. All right. So we have 2x equals x plus 3 minus 6. Why minus 6? Because we found out what b is. And that's this guy over here. Okay. So this was b. And now we can choose any virtually if you want. I would probably just choose 0 for here. So I can cancel the left side of the equation. Well, x represents any variables. You can choose any number. You can choose any number that you want. So plus 3 minus 6. And mind you, I chose 0 only after finding out what b is. Because otherwise, we can't cancel b from the get-go. As you can see here, by losing a over there. So we have 0 equals 3a minus 6. Well, this is just simple algebra at this point. And I'm just solving for a, which gives us a value of 2. Good. All right, so our partial fraction is now decomposed. Our fraction is decomposed now as a over x plus 3 plus b over x plus 3 squared dx. Insert new slide. There you go. Oops, not there. Yeah. Where was that? Okay, here. Any questions?
Yes,
All
can you
right.
please go back to the other slide?
Yes. Oh, this one.
Yes, thank you.
Okay. Alrighty. So for this, there is a particular sequence we tended to kind of like solve for b first before anything else. Okay, let me just erase that. Good. Let me know if you're ready.
Ready?
Continue. Okay, so let me just kind of like copy that. We have the integral of 2 over x plus 3. You can do a minus 6 if you want. Minus 6 over x plus 3 squared dx. Now, it looks like this was a lot simpler than the other page. But don't be deceived. Definitely this part here will be your ln case, your ln of x plus 3 with the 2 in front of it. However, this one is not because that's a square. So we might, we'll be using probably power rule here. And why does it fit the power rule requirement? Because you can write that as x plus 3 to the negative 2. Then we're also going to be using a little bit of U substitution. So that's why I'm saying that it kind of works better than the other one in terms of work. It's shorter, leading to this, but from there, you have a few extra steps to deal with. And the first one looks like it's done, but the second one is essentially this problem. Okay, so the squared here, make it into a -2. If we kind of do the reciprocal rule where you have a power in the denominator, you flip it, it becomes a -2 in the numerator. And we can just let u here, actually, just a different marker. So let u be equals to x plus 3. So du is, derivative of that is just 1. Oops. So that's just dx. So this becomes integral, well, I could throw a -6 out, u to the -2 du. And that would be plus 1 is -1 over -1 plus c, of course. So that will cancel the negatives here. So this thing here and that thing there. So far, so good. So this will be a 6 over u. If I flip back the -1 exponent, the u to the -1, it will go back to the denominator. The part will be x plus c. And now we can kind of like combine those answers together. So we'll have a 2 ln of x plus 3 plus 6 over x plus 3 plus c. And kind of like, any questions or violent reactions? Or I kind of miss the class. This is just too weird for me. Anyway, and it's too lecture-y. I mean, I normally would ask people to participate or write on the board. And good so far. Okay, because I'm going to be moving to the third case, but we're not going to be working the third case as part of the lesson. Most of the questions there would require very long minutes and hours sometimes just to solve. But I just want to show it to you anyway. So the third case is you have a quadratic denominator, as you could see there, a quadratic term. Quadratic term. Because you might say, isn't this one quadratic anyway, Mr. Ramos? Like this guy over there and that guy. That's true, but they are perfect square trinomials. You can write them as a something squared, so they're perfect squares. Now, the third case doesn't have a perfect square. It doesn't have it. It's just a quadratic term. And we know the linear term would have a constant in the numerator, but the quadratic term will have a linear numerator over here. Okay, so that's the difference. So if you have a quadratic denominator, which is non-perfect square, that has a linear, kind of like linear version of the denominator. Okay. All right. We're not going to be focusing on this one and probably just deal with it. I'm not sure if this example is part of your group work, so I'm not going to solve it right now. You're not supposed to solve them anyway. You can see there. You just need to set it up into what kind of integral that would become. So in the breakout session, I'll kind of like stop here at the moment. And for the group work, just kind of like to let everybody know what's going on. You will have for group work. It's part 1 and part 2. Those are 2 questions. They're not the same amount of points. One of them has more points than the other because one you have to solve and one you don't. And you can also, you see that when it's due, or when it's, yeah, I think that's the due date. I'm not sure if that's a due date because I probably took questions I have to take kind of like a Canvas. Did I lose the Canvas page? Oh, here.
Professor, we have no
Can you
idea.
see this? Can you see this on your screen? I mean, my Canvas. Okay, so student view, because it will look different from your view. So before I stop recording, I'll still be online. I'm gonna wait for you to kind of like if you have some questions, because we have some time to. Okay, so let me see. Go back to the student view. Okay, so this is what you'll see. Definitely what you'll see on your screen. And you have modules here. So you click modules. And you see that, oh, okay, it's March 23. My bad. So it's due on March 23. Telling you about. So it's a 5-point question. You just need to write the breakdown of this. Okay, so what kind of partial fraction will it become right here? Okay, so you can take a picture on your piece of paper. You can upload it. There is a submit assignment here on top. You can submit the pictures there. You can't see your group work. You're already randomized. I will group you into randomized groups. You won't see the answers of your classmates until you put your own answer, and then you can start correcting other answers from your group, so they can earn correction points from them. Okay. So that's the first one. You have up to March 23. That's a lot of days to complete this. I suggest you do it while it's fresh. And there's a second group work, which is the actual integration. Okay. Oh, TV is so loud downstairs. I could hear it. Okay, so this is the integration by trig substitution, and this is how I will be grading it. All right, so okay, so let me just stop the share of the screen and stop recording, and then you can go straight to